Welcome to Chemistry 111. Today we're going to go ahead and finish up, work on last year's test, so we get a good idea of all the different types of problems to expect to see and how to do it. Don't forget, the test is next Thursday. I'm going to send an email out to remind everyone. If you don't think you can make it at the test time like we did last time, work something out ahead of time. Say like, blah, 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 I can't make it because of sports. I mean, I got someone in my other class who's on the bass fishing team, and they'll be gone pretty much most of the week. They've already told me, and we've worked something out. So don't come like, oh, what was supposed to be at the test? Let me know. Take it a little bit early, take it a day late. Don't really care. I just want to get it done. Okay, so but we'll look at last year's test. We had already finished problem 1. We had previously solved the problem of gold chloride reacting with sodium metabisulfite, which was just a standard grams to grams conversion. So grams to moles to moles to grams. This one, number 2, is very similar. But it takes it one step further in that we're asked to find a percent yield. So we're going to have to turn grams of potassium chlorate into grams of potassium chloride and then determine the percent yield. Noting that we start with 38 grams of KClO3, and for every 2 KClO3s, we're going to get 2 KCl's. And the product is 20 grams of KCl. Okay. We got all we need to solve this. We might have to, of course, look up the molar mass, but that is something that can be easily done. So, almost always going to be starting with a mass over 1. Starting with one of our starting numbers over 1. Grams to moles. We need to figure out what is the molar mass of potassium chloride. Potassium is 39.1. Chlorine is 35.45. Oxygen is 16. There are 3 oxygens. So that means the molar mass is 122.55 grams in 1 mole. KClO3. So I've divided by grams to cancel out grams. I need to figure out what is the theoretical yield of KCl. So I'm going to turn this 2 to 2. For every 2 moles of KClO3, we have 2 moles of KCl from the balanced chemical equation. That will simplify to a 1-to-1 ratio, so we don't actually have to do that math, but if you want to strain your brain, go ahead. And then the last one, we need the molar mass of KCl. And 1 mole of KCl, how many grams do we have? Well, 39.1 and 35.45 leaves us with 74.55. Okay. Now, so we have our numbers set up. Let's convert grams of potassium chlorate to grams of potassium chloride. 39 divided by 120. Sorry, what am I doing? That's 38. 38 divided by 122.55 times 2 over 2, which is the same as times in 1, times 74.55. So the mass we should have got was 23.12 grams. Now, percent yield is simply actual divided by theoretical times 100 to turn it into a percent. So I'm just going to say 20 divided by 23 is going to give us 86.5%. However, just looking at that number right there, I can quickly tell which of these four options looks closest. 43, that'll be about 10, 12 grams. These are about 10 and 12 grams. All the 86 is the obvious number, even without doing the final math. Now this one looks really, really hard, but if you understand the first law of essentially the idea that everything must be conserved, it's actually really easy. Oxygen is scarce. Human muscles can convert glucose to lactic acid for a quick burst of energy. So glucose, which is C6H12O6, to 2 molecules of C3H6O3. So it split the molecules in half. If 328 grams of glucose were fermented in this way, how many grams of lactic acid could be formed? Now notice, this is splitting apart into 2 identical molecules. No new mass is coming in, no new mass is coming out. 100% of glucose is being converted into lactic acid. I'm going to go ahead and show the math, but note that if 100% of this is being converted to lactic acid without any new masses being introduced, the answer right there is obviously 328. There's a reason I didn't give you a multiple choice. I didn't give them a multiple choice because 328 grams of our starting material would be converted into 328 grams of lactic acid. But okay, let's look at that. Hypothetically, we look at the molar mass of glucose, C12, so C6, 12 times 6, plus 12 plus 16 times 6. 180 grams per 1 mole. Now, for every 1 mole of glucose, we produce 2 moles of lactic acid. And then C3H6O3 would have to be the molar mass of lactic acid would have to be 90 grams. So when you all said and done, you have 328 divided by 180 times 2 times 90. 2 times 90 is 180. So what do you have? 180 divided by 180, or essentially multiplying by 1. Had oxygen be introduced, it would gain mass. Had oxygen been lost, it would lose mass. But because it's literally, this is converted into this without any change, without any loss of material, it's 100% the same mass. 100% the same mass. Same total number of atoms, same mass. So that was a tricky one, meant to kind of make them think a little bit. Okay, anhydrous magnesium sulfate can absorb moisture to become hydrate epsomite, also known as Epsom salts. So in the following formula, MgSO4 plus 7 waters will form a compound MgSO4 dot 7 waters. If And I give you the molecular formula in case that thing is confusing. So MgS1H14O11. But if 15 grams of water and 15 grams of magnesium sulfate are mixed together, how much Epsom salts, pure Epsom salts, could be formed? This is a limiting reagent problem. So to do this, we need to find what I mean, the easiest way to do this is just go grams to grams one time and then go grams to grams a second time. And the important thing is to choose the smaller number. Choose the smaller number. So let's go ahead and go 15 grams of magnesium sulfate. Magnesium is 24.3. Sulfur is 32. Oxygen is 16. There's 4 oxygens, so the molar mass is 120.3. Now, for every 1 mole of MgSO4, we would have 1 mole of, let's say, Epsom salts. Now, the molar mass of Epsom salts would be the molar mass of magnesium sulfate plus the mass of 7 waters. So 120.3 plus 18, which is water, times 7. So the molar mass of an Epsom salt is 246.3 grams. So 15 grams of Epsom salt of magnesium sulfate could, in an excess of water, produce 30.7 grams of Epsom salts. Now let's look at from water's perspective. 15 grams of water. The molar mass of water is 18 grams for 1 mole. And then 1 mole, there needs to be 7 moles of water per 1 mole of Epsom salts. And because I already did that, 1 mole of Epsom salts weighs 246.3. So 15 divided by 18 divided by 7 times 246.3 would give us, well, that's going to be 29.3 grams of Epsom salts. Looking at this, we have to choose the lower of these 2 numbers. I know it says what is the maximum amount of Epsom salts that can be produced, but the maximum amount is controlled by the limiting reagent. So which is the limiting reagent? Water. Water maxes out at 29.3. This is assuming 100% yield. So the correct answer would be A, 29.3, not the 30.8, which would come if magnesium sulfate was the new reagent. Okay. Too much. In lab problem. Though if you didn't come to lab, you didn't do the lab, you can still do this because this is just a M1 V1 equals M2 V2. But you do have an advantage in that we did this same mathematical process. In lab, we diluted 10 mils of vinegar to 50 mils of vinegar. So we made a dilute vinegar solution. Then we titrated 12.5 of that dilute vinegar solution with 0.125 molar NaOH. If it took 22 mils of the base to neutralize the dilute vinegar solution, what is the concentration of the original vinegar solution? And I'm writing down these little facts so that I don't have to be jumping back and forth. So, okay. Already. So, our two equations are essentially the same equation done twice, just with different numbers. The first equation is M1 V1 equals M2 V2. We took original concentration, which is what we want to find, took 10 mils of it. We diluted to 50 mils. Because of that, that's going to be our M2. That's our dilute vinegar. Now, the dilute vinegar is going to be titrated. So we're going to call M2 also equal to MA. The other equation is MAVA equals MBVB. The idea that at equivalence point, when acid and base are equal, the moles of acid are equal to the moles of base. If I know the moles of base, I can thus know the moles of acid and thus figure out the molarity. So we took 12.5 mils of the acid, the VA. We took the 0.125 molar NaOH, which is our base, our hydroxide producer, and it took 22 mils of the base, our VB. So with this in mind, we have to find what is MA or M2 first. So it's going to be 22 times 0.125 divided by 12 and a half. You do that, M2 is going to be, let me rewrite this. So what I've just done is going to be equal to 0.22 molar. That is the first answer. However, we do not stop there. We plug that into here because that's our M2. So our M2, our M1 will thus be 50 times 0.22 divided by 10. So times 50 divided by 10 is the same as times 5. So our original concentration would be 1.1 molar. Now I know I'm giving you these volumes in milliliters, but as long as they're both in milliliters, it does not matter. Milliliters cancels milliliters. Liters cancels liters. As long as they're both in the same units, they cancel out, you're just fine. So correct answer is 1.1. I gave them a benefit there that I didn't put 0.22 as an answer. So they wouldn't then totally spaz out on that. Now this one is a little bit harder. Well, no. This one is we're going to take molarity and turn it into a mass instead of a mass into a molarity. The idea is we can go grams to moles to molarity, but we could also go backwards. So we have the molarity of barium hydroxide, 0.237 molar BaOH2. And we use 0.141 liters. With that in mind, so we got step one. Moles are equal to mass, molarity times volume. So our moles of barium hydroxide, 0.237 times 0.141 liters. 237 times 0.141 gives us a small number, but that is okay. 0.33417 moles. Now, I could have done this all as one equation, but we're working with what we got. And so we want to turn this into grams. What is the gram? So we have to find what is barium real quick. Barium's kind of heavy. I don't really remember barium right off the top of my head. Don't use that one nearly as much. Barium is 137.3. 137.3. And hydroxide is 17, and there's 2 hydroxides. So the molar mass is 171.3. Take that by our moles. And that would give us grams of barium hydroxide. That would be 5.72 grams. So notice I went molarity to moles and then moles to grams. It's a standard, straightforward process right there. So 5.72, that's our correct answer. You'll notice right now, so far, this has been very front-loaded for the chapter 9. We'll eventually move on to chapter 10 and 11. But what is the concentration of solution if 27 mils of sodium chloride, 27 mils of water are added to 23 mils of 0.25 molar sodium chloride? So this one is a little bit trickier because you have to, it's not straightforward. You have to think about what's being done. So 0.25 molar, and it's 27 mil, it's 23 mils. So when 27 mils of water are added to a solution, what happens to the volume? The volume goes up. I don't say enough water to make the volume 27. I say 27 mils of water are added. If there's already 23 mils of water and I add 27, the total volume is now 40, well, actually 50. It's 40 plus 7 plus 3, so 50 mils. So we have our situation just coming forward of, once you figure that out, it is incredibly easy. 0.25 times 23 equals M2 times 50. This is a simple dilution. Simple dilution. So 0.23 times 23 divided by 50, it goes to 0.1058. 1058. There we what goofed up? What got goofed up? Oh, I know. Jeez, I screwed up. I said, when I typed in my calculator, I did 0.23 times 23 divided by 50. So not 1058, but 115.115. So C. Now it's just a calculator error. And hopefully, most of my answers, you should be able to get the number pretty darn close. So looking back through, checking your work is usually pretty good. Antacids such as aluminum hydroxide are used to neutralize excess stomach acid in the reaction aluminum hydroxide plus 3HCl, aluminum chloride. What volume of 0.0316 molar stomach acid could be neutralized by 15 grams of aluminum hydroxide? So in this case, we have to approach this from both sides. You have to go 15 grams of aluminum hydroxide to moles. We need to get to moles of HCl. And we need to then use the moles of HCl to find the volume of HCl. So this one, not all of them are super easy. Some of them are meant to be challenges. 15 grams of AlOH3. I do believe aluminum's 27, but I will double check. Aluminum, close enough to 27. And once again, as I said, hydroxide is 17. There's 3 hydroxides, so 78. So there are 78 grams per 1 mole of aluminum hydroxide. And for every 1 mole of aluminum hydroxide, it reacted with 3 moles of HCl. So how many moles of HCl could we react with? This would react with 0.57, we'll say 577 moles of HCl. Now we need that moles equals molarity times volume. Oh, sorry, it's slightly off the screen. So if I were to solve for volume, I would say moles divided by molarity equals volume. So I'm going to take our 0.577 moles and divide by our 0.0316 molarity, which is moles per liter. If I do that, I will get our volume in liters. So if I put in 15 grams, it would react with 18.3 liters. 18.25, 18.3, a large amount. So answer is D. Okay. This is a Hess's law problem. How much energy could be generated through the fermentation of glucose? So we're going back to the original problem. C6H12O6 goes to 2C3H6O3. And I'm given 2 reactions. This is a Hess's law problem. Whenever you get 2 or more full reactions here, and I'm asking you to find a third, we have to use these 2 reactions to give us our answer. Now, to do this, the easiest way is to look what appears in the final reaction that appears in one of these reactions and use that as our guide. So glucose only appears in reaction 1. So I'm going to write reaction 1 exactly as it appears. C6H12O6 plus 6 oxygen goes to 6 CO2 and 6 water. And that has a delta H of negative 2805. Now the other one, lactic acid C3H6O3, is half as much and on the incorrect side of the equation. This is a reactant, and I want this as a product. This is a reactant, or this is 1, and I want this to double up to be 2. So I'm going to flip this over and double it. So what I mean is I put a 2 in front of, I multiply everything in here by 2, and I flop them to the other side of the equation. So 3 waters becomes 6 waters. 3 CO2 becomes 6 CO2. That yields 2 lactic acids, and 3 oxygens becomes 6 oxygens. And because I've done that, the delta H flips the sign, so negative 1344 becomes positive 1344, and because I doubled it, I would double the energy. So positive 1344 becomes 2688. Now I'm going to go to the document camera. I wanted to wait until we fully looked at that before I went to the document. So now I'm going to add this equation to that equation. Everything that appears on both left and right gets canceled out. 6 oxygen on the left cancels with 6 oxygen on the right. 6 CO2 on the right cancels with 6 CO2 on the left. 6 water on the right cancels with 6 water on the left. So the overall equation is C6H12O6 goes to 2C3H6O3. Now, as I've added both equations together, I have to add both of my delta H's together. So negative 2805, and we add 2688 to it. So the delta H for this thing is to produce negative 117. So negative 117 kilojoules of energy. So burning glucose gets a lot of energy, but when we need oxygen to do that. We need oxygen to do that. If we don't have oxygen, we can break it down into lactic acid for a short little burst of energy. It's not much, but it's enough to keep everything running. Hess's law, you have to look and see what appears in the final equation and try to match your individual equations to that. It's a little bit tricky, but we can do it. Okay, let's scroll down. Okay, 25 grams of unknown metal is heated to 100. Grams is heated to 100 and dropped into 30 mils of water with a heat capacity of 4.184. If the water goes to 28.4, what is the heat capacity of the metal? So what is the metal? Basically, the idea of this equation is heat capacity. The Qn equals Q out. Qn equals Q out. We say the Q of the metal is equal to the negative Q of the water. Q is equal to mass times heat capacity times change in temperature. So for the water, Q water, we have 30 mils, which is about 30 grams. We have a heat capacity, which is 4.184 joules per gram Celsius, and a final temperature, which is final temperature 28.4, and the initial temperature was, I think, 25. I can't remember. Let's see. Yeah, I think it's 25. So our change in temperature is 3.4. So looking at that, the heat of the water is equal to 426 0.768. Now the heat of the metal would be negative 426.768. We have 25 grams of metal. We have an unknown heat capacity, and we have a change in temperature. The change in temperature, the final temperature of the water is equal to the final temperature of the metal. So 28.4 minus 100. That's going to give you a negative change, but that matches a negative heat. So we have a negative change of negative 71.6. So negative 426.78, 768 divided by 71.6 and divided by 25. You do all that, you will get the heat capacity is equal to 0.238. 0.238. Now, looking back at the word document, the closest one to that would be silver, 0.235. So silver, 2.3. Okay. Okay, so what would the delta H reaction for the formation of 1 mole of potassium chloride in the following reaction be? So in this particular one, it's merely a products minus reactants. Products minus reactants. We have to sum up all of our products and sum up all of our reactants and subtract the two. So I'm going to write them down. Negative 435.9, positive 90.4, positive 33.9, and negative 391.4. Okay. Looking at this, going to the dot cam. Sum of all the products. All the products be negative 435.9 plus 90.4 times 3. 9. You get negative 164.7. That's our products. Our reactants, negative 391.4 plus 33.9 times 3. Is negative 289.7. So we get negative 164.7, which is our products, minus a negative 289.7. So minus a negative is the same as adding a positive. Our answer is 125 kilojoules. Positive 125 kilojoules. So answer C in this particular case. What would be the enthalpy of the reaction for the formation of boric acid when you dissolve boron trioxide in water? So just more of the same. B2O3 plus 3H2O goes to 2H3BO3. So just write the numbers down. Negative 1273.5 HbO3 is negative 1094.33, and that's negative 285.83. Okay. So to do this, once again, products minus reactants. So products, negative 1094.33 times 2 is 1094.33 times 2 is negative 2188.66. Our reactants, negative 1273.5 plus a negative 285.83 times 3, because there's 3 waters, is negative 2130.99. So negative 2188.66 minus a negative 2130.99. The energy of this reaction will be negative 57.67. Delta H reaction is literally, you find the sum of all the products, you find the sum of all the reactants, you add them up, you subtract the products from reactants, you get your answer. This is what it'll be like on the test. What it should be like on the test. So a gas expands inside a container while cooling by 300 joules. If the change in internal energy is negative 450, how much work was done on the system? This one was a little bit trickier wording, but it's the basic delta U equals Q plus W. Delta U equals Q plus W. So if gas expands while cooling by 300, so it's telling you when it cools, heat is lost. So we'd have a negative heat of negative 300. They say the internal energy is negative 450. So what must work be to make this math add up? The fact that I already said it expanded, when gases expand, they do work. But to have 450 equals negative 300 plus what? Work has to be negative 150. So negative 150. Just meant to have you think a little bit. It's supposed to be somewhat easy. Hopefully it wasn't too hard. Now, obviously we're not going to finish all this today. We'll go ahead and do one more problem and continue on this on Monday. Maybe a second problem if we can get through 15. In order to forge weld 2 iron bars together, the metal needs to be heated to 1260 Celsius. If the heat capacity of iron is 0.449, how much heat is required to go for 141 grams of iron from 25 degrees to forge weld? So temperature final is 1260. Temperature initial is 25. Mass is 141, and heat capacity is 0.449. So, with that in mind, Q equals MC delta T. We have 141. We have 0.449, and we have 1260 minus 25. Not meant to be difficult. This one's meant to actually be somewhat simple compared to some of the others. And so you would get, a really big number, 78186 joules, which you may have to turn into kilojoules. So divided by 1,000, it becomes 78 kilojoules. So the correct answer is C. Finally, finish off for probably today, define a state function and give an example. A state function is a function that is path independent, meaning you can calculate it through multiple different ways and still come out the same result. It was something where you can just use the final value and the initial value, and you can calculate the correct answer each time. Hess's law shows what it means to be a state function. But the good example of then a state function would be enthalpy. Enthalpy is the big one we hit largely this chapter. But as I said, you're not going to see this defined thing again on the homework. On the test. So you don't need to worry too much about that one. So let's look at what we have left. We will continue on Monday, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more problems, all dealing with gases. 10 more problems, all dealing with gases. But we will talk about them more on Monday. Okay. Thank you for your time.